Imagine a tiny game at a fair. You press a button, and one of three lights turns on. A blue light pays $0, a green light pays $2, and a gold light pays $8. Before you play, someone asks, what result should you expect? It is tempting to point at one prize. Maybe $2 feels typical. Maybe $8 feels exciting. But expected value is not a prediction of the next play. It answers a different question. If we could repeat the same game many times, what would the average result settle near? That long-run average is the idea we are going to build, one picture at a time. Let us play once. Suppose the gold light appears, and we win $8. Was $8 the expected value? No. That was only one result. Play again, and perhaps we get 0, then 2, then 0 again. Individual outcomes jump around. They are noisy, and they can be far from the long-run center. Think about taking one photograph of a busy street. That photograph is real, but it does not describe the usual traffic all day. In the same way, one play is real, but it does not reveal the average behavior of the game. To see that, we need repetition. Now keep a running average. After the first play, the average is just that first prize. After 2 plays, add the 2 prizes and divide by 2. After 3, divide the total by 3. Early on, every new result can move the average a lot. An $8 prize makes it jump. A $0 prize pulls it down. But as the list grows, each new result becomes one small part of a much larger history. The average still wiggles, yet the wiggles get smaller. Repetition does not make the outcomes less random. It makes the average more stable. Watch hundreds of plays. The blue light appears about half the time. The green light appears about 3 times in 10. The gold light appears about 2 times in 10. The exact counts are never perfectly neat, but their proportions become steadier. Because the same game is repeated under the same rules, the mixture of outcomes begins to resemble the probabilities built into the game. The long-run average then settles near $2.20. It may sit a little above, then a little below. The point is not perfect equality. The point is a clear destination around which the average keeps hovering. Here is a way to see the probabilities without any formula. Imagine 100 equal tiles. 50 tiles are blue, so half the space leads to $0. 30 tiles are green, so 30% of the space leads to $2. 20 tiles are gold, so 20% leads to $8. Choosing one random tile is the same kind of experiment as pressing the button. Over many choices, the larger regions are visited more often. Probability is simply telling us how much long-run attention each outcome receives. A prize matters to the average only in proportion to how often its region is reached. Let us turn those 100 tiles into money. The 50 blue tiles each contribute $0, so together they contribute 0. The 30 green tiles each contribute $2, giving $60. The 20 gold tiles each contribute $8, giving $160. Across 100 representative plays, the total is $220. Spread that total evenly across all 100 plays, and every play gets $2.20. No single play actually has to pay that amount. It is the equal share value of the whole repeated collection. There is another useful picture. A balance beam. Put the possible prizes at 0, 2, and 8 on a number line. Now place more weight where an outcome is more likely. A large weight at 0, a medium weight at 2, and a smaller weight at 8. The beam balances at 2.2. The rare $8 outcome pulls the balance to the right, but it cannot pull the center all the way to 8 because it happens only 20% of the time. Expected value is a probability-weighted center of the possible outcomes. Now that the pictures are familiar, the formula is just a compact description of them. For each possible outcome, multiply its value by its probability. Then add the contributions. 0 times 0.5 is 0. 2 times 0.3 is 0.6. 8 times 0.2 is 1.6. Add them, $2.2. In symbols, the expected value of x equals the sum of each value x times the probability that x equals x. The multiplication means how much this outcome contributes. The addition means collect the contributions from every possible outcome. A crucial warning: $2.20 is not a promised payment. Our game can only pay $0, $2, or $8. The expected value can sit between possible outcomes, just as the average number of children per family can be a decimal even though no family has a fraction of a child. Expected value describes a collection, not a guaranteed individual case. It also does not say that after a run of zeros, gold is due next. If each play is independent, the button has no memory. The long-run average can stabilize while the next outcome remains completely uncertain. The average does not move toward expectation at a fixed speed. Sometimes a lucky streak keeps it high for a while. Sometimes many zeros keep it low. With 10 plays, the average may still be far away. With 100, it is usually closer. With 10,000, it is often very close. This is the intuition behind the law of large numbers. For repeated independent trials with a well-behaved average, the sample average tends toward the expected value as the number of trials grows. Tends toward does not mean reaches exactly, and it does not mean every short run looks typical. Expected value is powerful, but it is not the whole story. Compare two games. Game A always pays $2. Game B pays 0 most of the time, but occasionally pays $20. Suppose both have an expected value of $2. Their long-run averages match, yet the experiences feel very different. Game A is steady. Game B is risky and jumpy. Expected value tells us the center, but not the spread around that center. When decisions matter, we may also care about risk, worst cases, time, and whether we can afford many repetitions. Expected value becomes practical when we compare it with cost. Our original game returns an average of $2.20 per play. If a ticket costs $1, the long-run net average is positive $1.20. If the ticket costs $3, the long-run net average is negative 80 cents. We find net expectation by subtracting the certain cost from the expected payout. This does not guarantee profit on one visit. It tells us which direction the average money flow points over many repeated plays. Sometimes we know the probabilities first and compute an expected value. Other times, we observe many results and use their average to estimate an unknown expectation. The two ideas face each other. Probability predicts where repeated averages should go. Data shows us where the running average actually goes. With more good data, the estimate usually becomes steadier. But the trials must represent the same process. If the rules change halfway through, or if we only record exciting wins, the observed average can be misleading. Repetition helps only when the repetitions are comparable and honestly observed. Here is the picture to keep. Random outcomes bounce around one by one. Place them into a growing collection and compute the average after each addition. At first, the average moves wildly. Later, each new result has less influence, and the path settles near a stable center. That center is the expected value. We can see it as an equal share across many representative trials, as the balance point of probability weights, or as the sum of value times probability. Expected value does not predict the next result. It describes the average destination of many repetitions. When you see the symbol E of X, think, repeat, average, settle.